Zoom
And
record.
who is 1, 2, 3, 4?
Okay, record is on. So analog input, we can read gradients from 0 to the maximum voltage that usually is related from 0 to 1023 or 24 because 23 because 0 is already a number, so it's 1024 in range. And with outputs, we can do the same. We can put a gradient of power. The difference in outputs is making gradients of power is not easy as an on-off. It's much more complicated, and the hardware behind is completely different. So to do a gradient for an output, we do what is called PWM. That is really important that you understand what is PWM. Óscar will go really deep into that because PWM is how you basically control everything accurately. And if you understand what is the behavior of just one MOSFET, you understand what's an H bridge, a triple A bridge, a quadruple A bridge. And if you understand what is PWM, you understand the whole thing about analogs, digital outputs, etc., and analog outputs emulated via PWM. Because PWM is a type of digital signal to make an emulation of analog outputs.
Okay. Thanks.
Okay.
I stop sharing my screen. It's all yours. Or you want me to control the screen?
No, I can control the screen. Just let me. I was adding some couple of notes into my local version of the site, so I will push them after the class. Just let me review. Okay.
Óscar.
Yeah.
Just to be sure that they understand everything clearly, I think it's really important to explain what you state about the magnetic inductance on the wires, on the cables.
Yeah.
Like really focus on this.
Don't worry. I'm gonna start sharing my screen. Here. Okay. Can you see my screen?
Yes.
Okay.
Yes.
So at the moment, what you see in my screen is my local version of the repository. I will push last minute changes that I did like 5-10 minutes ago. But don't worry, they will be right after the class. Most of the stuff that you see in the repository already under output devices and FabLab VCN classes, the first link, output device class. This is today's class where you can find all this information. So output devices. This is, I think, probably one of the most interesting topics that we will see in the second term, especially because it will allow us to start making things moves and things react to the inputs that we give them and to the things that we sense, that we actuate, and we put a little bit of coding inside our microcontrollers, and then we will see how things react to what we coded and to what we are sensing. The first example here is probably something that at the moment doesn't really make any sense. This is like an alarm bell or a ring bell that is actuated electrically. You see, it's quite old, but in very short time, you will start seeing how this thing works. What I want you to realize is that even if we see this, when we see these things, these two, what we call coils, these are the fundamental items that we have to understand, and we have to understand the physics behind them, so that we can understand how the things move, how we actuate valves, relays, solenoids, motors, steppers, etc. So what we are going to see today is different types of outputs. Tomorrow, Edu will give you a very nice introduction into do-it-yourself outputs, and there will be very likely more principles covered in there. But today we're going to see mainly three types. The first type is electromagnetic, so outputs that are based on the induction of a magnetic field. We will see what a magnetic field is and how it's inducted in a moment. Here we could talk about solenoids, motors, either DC, brushless, servo, or steppers. We'd also talk about electroluminescence. So when we create light from electricity, for example, LEDs or screens. And finally, piezoelectric, we create, instead of motion or light, we create sound. And in this case, we were talking about buzzers or speakers. So let's start with the first one. And the first one is electromagnetic output. And here, really the best we can do to know about this is to read Wikipedia. But I will make a digest for you of the things that you have to read. If you really want to understand this, you have to learn two topics. The first of them is called induction. Induction is basically a phenomena in physics that occurs when current goes through a wire, any wire, and it creates a magnetic field around it. Basically, if we go here to the link, so this was discovered by a guy called Faraday. And when you have current going through a wire, it will, sorry, let me find a better image. Wire induction. So when you have current going through a wire, this wire will generate a magnetic field. And depending on how you put the wire, in this case, we're putting in the shape of a coil, you can modify the shape of that magnetic field. What is a magnetic field? A magnetic field is a field that basically creates an area in the space around in which positive poles or north poles are attracted to opposite poles are attracted, and similar poles are repelled to each other. So this is very important, and you know already the physics or this relationship from when we talked about electricity and electrons and everything. But basically, when we create a magnetic field, is that we are creating an area in the space that has polarity, that has one area that is positively charged and an area that is negatively charged. And if we have a magnet that has a positive pole and a negative pole, the negative will be attracted to the positive, and the positive will be attracted to the negative. And basically, since we have this phenomena of induction, that we can control the magnetic field because we put electricity into a wire, then we can create what we see here in this image, which is basically a very simple representation of a motor. In here, what we see is that we have a coil on the left side and a coil on the right side. As we know already, when we put current through these coils, we will have a magnetic field around them. And if we put a magnet in the middle, then that magnet will tend to align itself to the north and the south poles of the coils, and basically will be generating motion from the by inducing this electromagnetic field in this area, and then placing a magnet inside of it. This magnet can be a magnet that you create also with electricity, or can be a magnet that is naturally like that. You all know that there are materials that have ferromagnetic properties, and then these inherently have these poles in them, so north and south poles, or positive and negative poles. Basically, I'm going to skip the PWM part for a second. Why do we put the wires like this and not directly straight? So let me come back to this one. Give me a second. I will put these images in the class. Give me a second. Okay. So here is what I was explaining earlier. Basically, you have this cable and you have a magnetic field around it. Why do we do this thing with the coils? So the thing with the coils is because you want to create a field that is a little bit bigger, and basically you just turn the wire into a cylinder so that you make a field that is wider and not just a circular field like this one here. Basically, to understand the physics behind it is like really a kind of intuitive thing to just relate to the concept of however much current you put into the wire, the stronger the magnetic field it will be. And that really lead us to start talking about motors, and seeing that this idea that we have in here, if we have two coils and a magnet inside, the stronger the magnetic field we have, then the more attractions we will have, and then the more torque we can generate. Torque is somehow the rotational force that we can have in the motor.
Imagine the coils as producing an artificial magnet with a coil, because when you polarize in one direction, it can behave the same as a magnet. So what happens when you have two magnets between each other? Like the north attracts the south one and the south attracts the north one of the other one. So with that, we can just have one movement.
Exactly. So now, if we want to have a lot of, so if we want to have more force inside our system, we have to increase the magnetic field that we have that we are creating with the coils. And for that, the only thing that we need to do is increase the current. That's why in motors that are based in this principle, when you increase the current of a motor, then that will increase the torque, simply because you are creating a higher magnetic field. However, that doesn't always apply in the real world, because these wires at the end of the day are physical wires that have certain resistance. And you know that when current goes through a resistance, it releases heat. And sometimes if that current is too high, then you might release so much heat that you can damage the wire. So of course you want to make these coils conductive, But when you have a motor and that you want to have a lot of torque, then those wires have to be thicker so that you can put more current through them without heating up the wire. And in that way, you can increase the size, by increasing the size of the motor, you can increase the torque. And that's why very small motors have very little torque that you can even stop with your hand or with your fingers, or much bigger motors can give you more torque because they can hold more current and without burning them. Finally, and just to relate a little bit on the concept of like how this links to motors, this could be at a certain voltage, higher or lower voltage. We are talking here always about DC voltage. We are not talking about alternating currents or anything like that. In this topic, we are always talking about constant voltage, but not oscillating. But what happens when we activate this in here, and we're making this move? So if you have your coils activated and you have these the magnets inside moving, there will be a counter force by the magnets when they have to align themselves with the coils. That is what we call it's a voltage that the field inside is a voltage that we're generating in itself by the magnets inside in the motor, meaning that these magnets themselves are generating voltage in the coils as well. And we have to somehow overcome that voltage that the magnets inside are generating in the coils so that we can make them turn. So the more voltage we put, the bigger the difference is going to be, and that's why the faster the motor is going to turn. So if you want to relate a little bit with properties of motors that come from electromagnetic fields, I think it's better to, it's a good idea to read these links that we have in the documentation and also read these paragraphs and try to not memorize the concepts, but to derive them while you're thinking. And understand that motors, how much torque they can develop, it depends on how much current you put inside of them, because it depends, the electromagnetic field that you create with that current will be stronger. How much current you can put, it depends on the size of the coils. If you have a small coils or thinner wires, then you will have a lot of resistance, and that will make your motor to burn. If you rush in too much current, and basically it will start smelling and it will halt. Always remember basic laws of physics, especially Newton, that when you push with one hand and to the other, they have counteracting forces that are on opposite sides. And this is the same with motors. So if you have a motor, the motor will only give you a force that is related to the load that it has. So if you hold the motor with your hand, if the motor is strong enough, it will try to overcome and twist your wrist. But if the motor is too small and you hold it with your fingers, probably you will even stop it. And the current that you have to put in will have to grow so that you have a stronger magnetic field. But of course, every motor has a limitation, and that's what we call the stall current. It is that the maximum current that you can put in the motor without burning it. And finally, remember that when you have a motor and you have a magnet moving inside between two coils, that magnet is generating also a magnetic field in your coils. And so that you can keep the magnet still rotating, then you have to increase the voltage. If you increase so much the voltage that the magnet can keep rotating even faster, then you will increase the speed. So voltage is related to speed, current is related to torque. I think probably Let me see if there was here something. Probably, Edu, you can play your video of the of your tests with the little coils.
It's in the DIY outputs. It's
Okay,
uploaded in the class.
So let's try to understand very quickly, and we jump a little bit to PWM. Oh, sorry, it's not this one.
Down.
This one? Oh,
Well,
well, this one is a good example already. So
actually, Oscar, if you go onto my video, it's clearly easy to see because the motor only rotates one side because there is no change in polarity.
is this one?
No, down. I wish it was that nice video.
This one. Okay.
Yes.
Okay. So what Edo has here is a battery. The battery is supplying a difference in voltage in between between both sides, and then there's a cable that we have made into a coil. Under here we have a magnet, and the magnet is static in this case. So you see that we are generating a magnetic field with this magnet, and then we are also generating another magnetic field in the coil because we're putting current through it. So in this case, when you put current through the coil, the wire will start rotating, but you see that it aligns itself with the well, there are two things happening. First of them is that we see some little sparks on the side is because we have a short. Can you mute, Edu? Sorry. And the other thing is that at the end you see that the coil is aligning itself with the magnet because there's no way for the coil to have an alternating. There's no way for the coil to have an alternating magnetic field, and at some point, if the coil has a magnetic field aligned with the actual magnet that we have in the bottom, then both of them will become static and they won't keep rotating. If you want to make that so that the coil spins forever, then you have to stop flowing current on one side of the wire and make the magnetic field either cancel it or flip it so that it aligns, it keeps turning and tries to align itself again with the magnet. But in this case, this is not happening, so that's why at the end it stops. Okay, I know that this is a little bit probably complicated. Do you have any questions until now?
I have seen that sometimes it needs like a little help in the motor to start rotating it. Is there any way to solve it? Like, I don't know, to give more power in the beginning and then lower the power down? Or...
Yeah, exactly. So so the motors, how they work at the beginning is that they have to overcome their own inertia. So it's like when you are spinning or when you are on the bicycle at the beginning, it's a little bit more difficult for you to start going. But then when you're going fast, you can still keep pedaling, and the effort that you have to do even for going so fast is not the same as the one that you have to do when you started like kicking off, let's say. And that's why, because you have to overcome your own inertia. And at the beginning, the motors don't have enough force or enough strength to start rotating and overcome their own the inertia of their own rotor. The inner part of the motor that is rotating is called the rotor. The outer part is called the stator. So the rotor has an inertia, and sometimes it's a little bit difficult to overcome that. How can you counteract? How can you make that? Either you help it by hand, or you put more current. but putting more current sometimes is not easy, because your electronics or your circuit cannot give you more current because it's limited by that. So you have to help things a little bit. After you overcome the inertia, then the current goes down and you get to what we know the running current, which is the current that the motor needs to run at normal speed without any load. And this totally makes sense with the previous part, because when you have more current, then you have a stronger magnetic field, and the stronger the magnetic field, the more torque that you can develop in the motor and overcome the inertia that it has when it's stopped and has to accelerate. Does that answer your question, Pablo?
Yeah, thank you. I also wanted to ask you, well, maybe you're gonna talk about it, about the opposite way of generating that if you do it backwards, if you move the motor, it also generates energy.
Yeah, exactly. So actually any motor can be a generator. And I don't know if you have ever, as a practical example, I don't know if you have ever seen in a 3D printer, when you move your, especially in the deltas, if you move the head by yourself, then you will be, and the printer is off, then you will be rotating the steppers by yourself, by hand, and that energy is going somewhere. It's going somewhere and it's turning on the screen, and it turns blue for a little while. It happens in my 3D printer at home and in the Anycubic that you have in the lab. And basically, yeah, a generator is exactly that. And for example, that's a principle that you use in turbines, like in water turbines or any turbine that you have, or any electric generator that we use nowadays to generate electricity. Is basically you have a motor, but the energy doesn't come from you putting electricity into the motor, but comes from you moving the shaft and that inducing current into the static part. How fast you move the motor, then it will affect on how much current you're putting into each of the coils and how much resistance you put into that movement. By creating a magnetic field, then you will create more voltage. And if you want to read more, a little bit more about this, if you go to the link in Wikipedia, here is explained how this was discovered by Faraday, and by using this pinwheel, this disc, that basically he was rotating with his hand and seeing a voltage. So this is more or less the same principle, and you see a voltage in this dial because you are moving with your hand the wheel, and that is generating a magnetic field that is then induced into electricity into your coils. So they're basically the same. Actually, in automotive and in trains, when you have electric trains and you want to move the train, you put electricity, but when you are braking, you use what we call regenerative braking, which is you turn the motors into a generator, and that puts a lot of resistance in the motor, so you are braking, and the motors turn into generators for a second, and they give you back the electricity that you put before to move the train. And with the inertia of the train, you can move the motors, and that generate electricity and put back into batteries, or if you have in the case that you have a car or an electric bus or something like that. And in just as a side note, if you are very, very smart and you know, for example, that you have a train, or that you have, for example, a bus, and that in 100 meters you have a bus and you're going up a slope, and you have to put electricity, you might also want to plan a little bit ahead, and knowing that you're going to go down a slope and that you're going to recuperate energy, and for example, use that energy that you are taking, that you are using to climb up the slope, to then recuperate it when you go down, and using your motors into putting energy back into your battery. So that is broadly done. And yes, any motor can become a generator. The only thing that changes is the direction of the mechanical energy. Let's say, if it comes out of the motor or if you put it into the motor. Okay, so coming back to the this other part. Now it's a little bit easier to understand what's going on in here. So you see here that we have a closed circuit. Basically, we have a voltage source on the right side. We are passing currents through coils. Here you see that the coils are inverted, so we are generating a magnetic field. And that magnetic field is attracting a metal part, a metal element, when the magnetic field is generated. And that metal element is also attached to like a thread that is acting as a switch. So when you have contact, you are closing the circuit. But when you don't have contact because you moved the metal plate by activating the coil, and that the coil activation is because the circuit is closed and there's current flowing, then when there's no contact, you open the circuit and then it comes back to normal position. And that's basically used to ring bells and alarms and things like that, and that's what you're having here. So these two things are coils. They are inversely magnetized, and here you see that they are attracting this metal plate. This metal plate, when attracted, is hitting this bell. And in here, when the metal plate is, let's say, in relaxed position, it's not being attracted, this closes the circuit. But when it closes the circuit, then, when it being attracted by the coils, then it opens the circuit here, and the coils are not energized, and therefore they open the circuit and come back to normal position. And that's basically, so if you understand that when you put current through a coil or current through a wire, it generates an electric field, then you will understand as well, not only motors, but also solenoids. Solenoids are the exact same thing. And the only thing is that you have them put with like in the shape of a spring, and the magnetic field that you create goes as seen here in the picture. The only thing is that when you put something metallic inside that coil, that will also polarize, and then you can move it because that thing will turn to align itself or to be attracted to the magnetic field that you're generating inside. And that's how, for example, you use if you use that principle to open another switch, then you have a relay. So if you open a relay, and these things in here, the blue things, you will find just a coil that has basically a solenoid and a metallic part in the middle. In this case, when we activate the coil, we are attracting the metal plate on the top, and we are closing the circuit. When we don't activate it, then that has like a spring that makes it come back. And that's why, and this is the sound that you hear when you activate electromechanical relays.
For example, those electromagnetic relays is everything that you find in any mechanism. For example, electric doors, like of your house, or garage doors. Like most of the linear activation of simple mechanism that doesn't need too much load, they are done with your solenoids. Or even also like water closing valves. You know, you have a pipe and you want to close and open the valve, especially for gardening or like hydraulic circuits, they are done just with solenoids. But when you push your lineal, what it does is closes the pipe of water. Yeah.
If you look, and this is used everywhere, like literally, let's see.
Is from your laundry machine. Your laundry machine has usually like 3 or 4 of these, just to take the water in, take the water out, allow the water in, allow the water out, because it just uses the main pipe pressure of the water of the city, and just you need to do is like keep it open for a while and keep it off for a while.
Exactly, and literally, I mean, give me a second.
So meanwhile, Óscar is off.
No, I'm back.
Okay.
So this is not a pen, but as you know, well, I don't think I can open this. Well, this is, if you see in here, this is a diesel injector. This is this goes in a car in your engine. As you know, I was working before for the automotive industry, and don't tell anyone. But I took one of these as just to remember.
That's why you are not working anymore there.
Exactly. And here, this is the same principle. So inside here, you have a needle, a metallic needle. I will show you a picture in a second, but you have a needle in here that with very high pressure, at 2000 bars of fuel pressure, gets activated or not activated by moving a coil that is in this big part in here. And you can see here the two electrodes that will activate the coil. And here you see where the fuel goes in. This is the point that the fuel goes inside. And this whole thing is basically a solenoid injector, and that is used to put fuel inside the chamber of a combustion engine. If you see, for example, Bosch diesel injector principle, here, this is a piezo here. So you have the injector nozzle and the needle. Here you have high pressure fuel, and up here you see again solenoid coil. Basically here you have a coil that is activated with two wires, not very much energy to activate this thing. The coil, when activated, moves this plunge, and that makes a little bit of hydraulic balances inside the injector that opens the needle, and then it allows you to inject. The nice thing about this, about the injectors or the solenoids in general, is that they can be activated very quickly and very precisely, and the response is very fast. So you can use them for activating things, not only relays, but injectors, and with very high precision and with very high speed. There are other type of relays, and you might have heard about these things, like they are called SSRs, or solid state relays. Just as a reference, here they are not electromagnetic, but they are what we call, they do something called optocoupling, which basically you have a light sensor and an LED, and when it's not exactly like that, but you have a phototransistor and an LED, and when you turn off the LED, then the phototransistor is closed. When you turn on the LED, then the phototransistor is open, and that basically acts as a switch. And that's what you have in here. They have this body, and sorry, 1 second, is that the advantage of this is that they are very quiet, but the only problem is that as they don't rely on mechanical movement, they heat up a lot, and you need a little bit of heat sinks, let's say, to release all that heat. Sorry, yeah.
Sorry, optocoupling is something that you usually do when you have a really big difference in voltage or type of load. For example, in SSR are usually used for like allowing a switch transformation, let's say, from DC to AC, or for example, from DC like 200 volts and DC 3 volts, because there is a big difference in voltage, and that might create a lot of noise interference just because of the wires. As the wires being wire, you have a wire, the wire has electromagnetic interference, magnetic field is creating, and if you have a big difference, the big one will create a stronger magnetic field than the smaller one. So what you want is to have, like, let's say, a separated circuit physically. So what you do is transmit the instructions to open or close the switch with light.
Yeah. That thing that Edu's talking about is called galvanic isolation, which means basically you are separating electric levels on your circuit and that have very high differences, for example, in current or voltage, by not physically connecting them, but for example, connecting them with light. And in this case, what we call an optocoupler or an opto-isolator is basically doing a join between two circuits, but optically. For example, with lights, as we said, with a phototransistor, that is basically a transistor that is activated by light, not by electricity, and an LED in this case on the other side. And that's basically what you have inside a piezo, an SSR. If you want to see a little bit of comparison, there's a very nice comparison in Arrow's website, and here I put the table. Just to remember, I've used both in the past. I mean, and you will use both very likely. The most important thing is that electromechanicals are a little bit slower. They also make noise, and probably depending on the contraction, they will tend to fail mechanically after a lot of cycles and if activated very fast. The solid-state relays provide a galvanic isolation and probably are a little bit more reliable, but you really have to be careful with thermal management. It means that the opto-isolator will need to release the heat somewhere. And if you confine the relays in a very small space, they probably will melt because they have to dissipate a lot of energy by the operation of the transistor. The transistor I'm talking about is just here, this one here. Okay.
So just a bit of information about the standard blue relays that you might see in your Arduino kits. Those ones, for example, are rated for more or less 100,000 cycles. So if you activate more, all the devices are rated to a life cycle, some like life cycle, that how many times it can get activated and deactivated. So those ones, for example, that are, let's say, cheap relays, they are done for 100,000 cycles. And the speed of those ones, you can activate it each 200 milliseconds, let's say at the highest speed. So that means you can activate them on and off 5 seconds, but that will create a lot of noise, like clack, 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 because basically it's a metal solenoid hitting a metal plate.
Exactly, it's basically this, opening and closing all the time. Just a couple of things to take into account when you are selecting relays. Remember, the relays can be normally open or normally closed. It means normally open is when you don't activate them how they are, if the switch is open, or in the case of normally open, the switch is open always, and if you activate it, it will close, and the other way around if it's normally closed. And also importantly, you have to see the activation voltage. Normally they are activated by DC voltage, and depending on the size of the coil on the relay, the voltage could be 5, 12, 24 or more. And also the current that they can, let's say, interrupt. It's not the same to interrupt 10 amps than 200, because 200 amps, for example, could create an arch between the two plates just by ionizing the air between them and creating a short. And that depends also on the construction of the relay. And here, normally on the top of the relay, you see this information. So in the bottom part, you see that is activated by 5 volts DC, and that it can cut either 10 amps, 250 volts AC, 10 amps, 30 volts DC, 10 amps, 125, or 10 amps, 28 volts. So basically, you have some information of the ratings already written into that. And of course, if they are normally closed or normally open. Here you see on the left side, the screw connector. The common is, let's say, the ground, or the common point of your circuit, and on the left side you have NO normally open, NC normally closed. Means that if you don't activate or do activate, what is the behavior of the relay?
The SSR that you usually use, they don't work on the activated part on DC. They usually can go only activate AC current. They are only rated for AC. They don't work by DC. But for example, the mechanical relays, they can work with AC and DC.
The only other thing about solid-state relays is that normally they have quite a nice range of input voltage. So it means that They can be activated by very low or much higher voltage in the inputs. In this case, for example, you see that you can activate it from 3 to 32 volts, whereas on the mechanical one, you had only 5 volts. And that's it. If you have a voltage that is much lower than that, then like 3 volts, it wouldn't open because you wouldn't be able to activate the coil and not move the metal part inside.
And if it's small, what happens?
Sorry?
If it's more than 5 volts for the relay, is it bad or?
Usually you have a range of activation, and I have tested those ones until 3.3 volts, and they work. But you can get fake activations or not make it reach to activate.
Sorry,
Well,
so
if you
no, don't worry.
Pablo.
Okay, no,
Say.
what I was gonna ask is, so usually, because I'm when I have seen schematics about how to connect a water pump, usually they use a relay, but I'm not sure if I'm gonna need an external source of energy.
Yeah, so basically the relay is a switch, and the pump. So you will have the thing that that we see here, and probably we can see it in this image in here, is that we will have, and now we are starting to talk about these things, is that we will have a part of our system that is the control circuit and a part that is the end actuation circuit. The control circuit, it will have our Arduino, and is where we want the smart thing to be. The Arduino normally is going to be between 3.3, 5 volts. And we want to separate them both because we don't want our Arduino to get damaged because of what is happening on, let's say, the actuator part. The joint between those two parts is, in this case, the relay, but we will see in a second that it can also be a MOSFET or can be other things. In the Arduino side, as I said, we have a low voltage as 5, and that can be powered by USB or something like that. But on the actuator side, then it depends on the actuators that we have. For example, pumps can be at 12 volts DC and 1 amp, and that cannot be handled by the Arduino. So we need an external power supply that is able to feed enough energy into the pump, but we don't want that to be permanent. We want to control how that happens. And the way that we control that thing is by putting a relay, a switch, that we can control with our small electronics with 5 volts on one side, and that can manage high currents on the other. Does that make sense?
Yeah, so
here,
as I understand, the relay works, so the Arduino controls the relay to let it use higher voltage and current flows or sources.
Exactly. Yeah, exactly. Exactly. And it can be totally different types. So for example, you can control a relay that handles not only DC current, but also AC and 230, for example. And you can turn on and off a lamp, the normal that is plugged to the socket in your wall, by putting a relay in the middle that you control with an Arduino or a microcontroller.
Is there any way, because I have been struggling a lot of where to get the external power source for the relay, but is there any way I could control the pump with the Arduino without an external power source? These normal water pumps motors that they sell?
No, I mean you need to give them power unless, for example, you put a battery.
But imagine, Pablo, your Arduino doesn't have power pack. So how are you powering your pump, your Arduino? With the computer, no? The USB.
Yeah, with the
computer or a USB cable to the
phone charger.
A charger or something like that.
So actually your power supply in that case is your USB. And the USB usually is 5 volts, 1 amp. So if you cut the cable and you connect the 5 volts to the Arduino and another 2, you divide the cable in 2 and you connect another 5 volts, you will be rated to the maximum amperes and voltage that your power supply can handle. That is 5 volts, 1 amp.
Okay. Thank you.
So one of the first thing when you design an electronic output circuit is really try to know the data sheet on or the mechanical information of your output motors, because usually it's what takes the most out of the current of your circuit. Óscar, tenemos que acelerar un pelín.
Vale, perdón, ok.
No, yo también me lío, ¿eh? Lo siento, estoy cortando.
No, okay. So let's jump to the next part. MOSFETs, the big question here. What is a MOSFET? MOSFET is a type of transistor that have a specific construction in the semiconductors. I don't want to really go super into detail into semiconductors and these things, but basically keep in mind that there are different types of semiconductors. Semiconductors is a material that that conducts electricity, but depending on the external conditions, on how it is activated, it will conduct more or less electricity, or let's say it will have more or less resistance. Now, semiconductors can be of different types. I really recommend you to read this link in here, this core dump electronics, because it talks about semiconductors and MOSFETs really into deep. But I'm gonna make a very, very quick summary for this. So semiconductors, if you imagine a piece of material and you, that is a semiconductor, and you put electrons, so you dope the material and you put extra electrons inside the material, then you have a negative semiconductor, or what we call an N-type semiconductor. This means that is a material that can have, that has the semiconductor properties, but that all of a sudden became a little bit more interesting because has electrons inside that we put manually. If we do that on the opposite side, so instead of putting putting electrons, we remove electrons from the material, then we have a positive semiconductor or a P-type semiconductors. The interesting about semiconductors on itself is not how they are by themselves, but how they relate with each other. So, if you can imagine the N-type semiconductor, so the one that has electrons, and the P-type semiconductor, so the one that has less electrons, where do you think electricity is going to be easier to go? It will go easier from the negative to the positive, or the positive to the negative? It's an open question.
The positive to the negative?
No, because it will go from the negative N-type to the P-type, because we already have excess of electrons in the N-type. So
okay.
It's easier for electricity to go from the negative to the positive, but not from the positive to the negative. Good news, we have just discovered the diode, which is basically two semiconductors, N and P, together, and the electricity can flow on one side, but not on the other. Of course, that depends on how much electrons you put on one side and how many electrons you remove from the other side. And of course, when you have a diode, there's a limit in the electricity that you can put back, because of course, at some point, the electrons in the P-type semiconductor will start flowing back to the N-type semiconductors if you put a lot of voltage. Remember that when we put voltage, we are like forcing electrons, and they are being attracted to one side. So even if it's easier for the diode to conduct on one side, but not on the other, at some point, if we put a lot of voltage reverse, then it will end up flowing. And that's basically because of a semiconductor. What is a MOSFET? A MOSFET is three semiconductors that can be NPN or PNP. That's why you have different characteristics. So P-channel or N-channel MOSFETs that are put together and that have a metal plate on one side of them, in the middle part. And if you see here, this is an N-type MOSFET. And as we just derived or thought, we have more electrons in the N-type, less electrons in the P-type, more in the N-type. What happens if we put voltage on what we call the gate? Then we will attract electrons in the p-type area, and we will have protons or like a more positively charged area in the right side and negative on the left side. Means that we are connecting somehow both the n types, and electricity all of a sudden can flow from the top to the bottom, because from n to p is easy, but from p to n is not easy. But now we have created an accumulation of electrons on one side because we activated here on the gate. If we don't activate it, then this will be normal, and we will be able to flow electricity from n to p, but not from p to n, because this is, we could model this as a diode. It's not exactly that, but we could model this as a diode, more or less, just to understand it. And basically, when we want to transfer current from the top to the bottom and we are not activating this, then we have an open switch, or we have a lot of resistance. If we want to have a closed switch or very low resistance, then we put electricity in here. Magic, we have an electronically controlled switch that we can activate just by putting voltage in this gate. Now, you can, I think that you can have a read into this part in here. The most important part that you have to remember is, first, what is the voltage that you have to put between the gate and the source to activate the MOSFET? Means that the MOSFET, if it's a 5-volt MOSFET, it needs 5 volts between the gate and the source for it to activate it. And that is the activation or the drive voltage, and also the resistance that we have when we activate the MOSFET. And that is very important because, again, as you know, when we put current through a resistance, then it dissipates heat. And if you have a very high resistance because you didn't apply enough voltage, then there will be a lot of heat release. And that is, for example, very similar to what happens in the optocouplers, because you have to release the heat because these guys have resistance in here. So.
And one question, other than being a switch, I read that it also can like amplify the signals, but how would that work?
Amplifiers are also based on transistors, but it's not. But it's not in the application now. I think what we can do about that is, maybe if we have some time at the end of the class, we're going to talk about piezo and so piezoelectric outputs and amplifiers. If you want, we can talk a little bit about that at the end, but it's not only with MOSFETs. It's what we call an operational amplifier, which basically is using voltage reference on one side and a voltage reference on the other, and is mapping them both by using a combination of transistors inside. But it's but with this principle, I mean, it's not on the on this same principle, let's say. We will talk about at the end. Okay.
Do the relay and the MOSFET have the same function? And if so, why do we use a MOSFET instead of a relay?
Okay, so they can have the same function. They can be a switch in both of them, in both cases. The nice thing about the MOSFET is that you can have them in a package, let's say, which might end up looking like this. So you can put that into your circuit, and it will take a very small space, and they can really handle a lot of current. The thing about the MOSFETs as well is that you can control them very precisely and very fast, and you can also regulate the resistance that they have in them if you operate in an area that is not exactly on or exactly off. And we will learn a little about that in a second when we are talking about PWM. Basically, you are turning on and off the MOSFET all the time in a certain frequency. and the average voltage that you have while operating that will be reflected on the gate, let's say, and from gate to source voltage, and that will open on and off, and that will generate like an average voltage on the end side, and like that you can regulate, for example, the load that or the speed that you put into that you have in a motor. The important thing about MOSFET in this case is that you can put that into an electronic board and it doesn't take that much space, and also that you can control it much precisely than just a relay. At the end of the day, a relay is a mechanical component that has an inertia, that has that can vibrate, that can break, and a MOSFET is just a semiconductor piece that is much faster to control. So really have a look at this this part. The more typical ones of MOSFET are what we call N-channel MOSFET, which has the semiconductors, the N dopes and the N-type semiconductors on the end. But you can also have the P-channel MOSFET, and they are operated differently. So you have to be aware of this part, or where to put it. The N-channel MOSFETs, they are operated when we turn them on. Then we will have an on state, and the P-channel MOSFET is they're operated when they're turned off if we follow this schema. It's important that you put also this pull down resistor or pull up resistor so that the gate is not in a floating state after operating it, and that we can pull down or pull up to close or open in the MOSFET. And also remember that, well, when we have here the MOSFET, this is the voltage source of the load, let's say, so this will be 12 volts on this side and 0 volts on the other side. And here it will be the motor in this case. So this voltage here is different than this voltage in here. They are not equal, or they don't have to be equal. And that you have to think what type of MOSFET you are using so that you are able to turn them on or off. That also depends not only on the type of MOSFET, if it's N-channel or P-channel, but also if it's depletion or enhancement mode, means that it's normally on or normally off. So always read the type of MOSFET that you have. Very quickly, and we will start jumping into H-bridges and motors. Have a quick look at this cheat sheet. I find it very useful for understanding a little bit how the transistors and the MOSFETs work, and how to put them, and more the more typical types that you can find. Okay, we have these ones in the lab, if I'm not wrong, and a version of these ones as well. So imagine that we have this case. This here is our motor. We are controlling with, sorry, not this one, this one. So we have voltage, 12 volts, and the motor. If we always have this situation, then our motor will always work in the same direction. So current will go through from the positive to the negative, and the motor is always on the same way. So we are only able to control the speed of the motor by modifying the voltage, or the torque of the motor by modifying the speed. And probably Edu will talk about motor regulators in a while. But we cannot reverse the direction. So why do we use, what do we do with that? Do we have to make a separate circuit, or do we have to do the separate voltage? So we got you covered again by what we call the H-bridge. An H-bridge is a combination of transistors or MOSFETs that is done with two signals. And with two signals, you activate or deactivate certain types of, you activate or deactivate MOSFETs or transistors. And by that, you shape how the current flows into the motor. So if it goes from positive to negative or from negative to positive. And that way you reverse the way that the magnetic field is applied. And because of that, you reverse the direction. So as you see in here, when we activate the input A, then we will be activating this MOSFET in here. And when we activate this transistor in here, and the input B will be activating this input in here. So basically the current will be flowing like this, and the motor will turn in one direction. If we do the opposite, then we will turn the motor on the other direction. This can be made by yourself, even with relays. You could just build this by yourself, and I think that some MDEF students did this in the past in one of the Guillem's and Victor classes. You could do it with transistors, or you can buy let's say a package that already contains that. The most famous ones.
The graphic above where of the H bridge, there's arrows going into the MOSFET and going out. Is that what defines a P and N type?
Yeah. So, well, that's a symbol more or less, but if you go into here, it's not only the arrow going in, but where it goes. So you see in here, this is the the NPN transistor and the PNP transistor. That in one, the arrow goes from D to E, and the other one goes from E to D.
Okay.
And the MOSFET is this other symbol in here. And you see that N channel goes with the arrow in, the P channel goes with the arrow out.
Mm-hmm. So the NPN transistor is different than a MOSFET, or is it just?
No, NPN transistor is a transistor.
Okay, cool.
A MOSFET is a metal oxide semiconductor. So is a type of semiconductor that is made with a different type of material.
Cool.
Usually, just to have applications, to how to choose an application where to use a P channel and N channel. In a longer term, like P channel, as you need to pull it low from the high state, if the current that you are driving at the voltage is really high, for example, let's say you are controlling a circuit, a pump that is 24 volts and your Arduino is 5 volts, there is a big difference in voltage. As the Arduino needs to pull from 24 to 0, it will have a lot of troubles to pull that range of voltage, to pull it low. So on the other side, N channel, they don't have to do that. They have to do the opposite, pull it high. So actually, when you have a big difference in voltage between the driving circuit and the driven circuit, you want to use preferably an N channel MOSFET. If you have a more or less the same, more or less different in voltage, you can use a P channel MOSFET.
What I also recommend you to do is to have a look, because at the end of the day, this is. So I recommend you to have a look at these videos. When I learned about MOSFETs, this guy is very, very good at explaining, and the link you can find them in here, in this video in here. And he really goes to the details of N channel, P channel, the different constructions that you can put, etc. So here you have some configurations for MOSFETs. Really have a look at these cheat sheets so that you see how the different legs are configured and where you should put them, if you should put a resistor, a diode, or something like that extra. These are some recipes for the H-bridge. The H-bridge, remember that you can find them in this package for DC control, or that you can make them yourself with transistors or with relays as well. It's a nice experiment. And finally, just let me, before we jump into steppers with Edu, very quickly, let's talk a little bit about PWM. So where is this PWM? Here. So PWM is just a technique that we use to control an output with what we call an equivalent voltage. So imagine that we have an alternating voltage between 0 and 5 volts. If we have a lot of time 5 volts, for example, 90% of the time 5 volts and 10% of the time 0 volts, just switching from on to off, then our equivalent voltage, let's say on average, we will have 4.5 volts, let's say. If we reduce the amount of time that we are on with respect to the time that we are off, then we can decrease the average voltage that we have. Of course, if we do that very slowly, our system will notice that and will turn on and off all the time. But if we do it fast enough, and by enough we are talking about hundreds of kilohertz or fast, then we will have an average voltage that is perceived to be almost continuous, but at a lower level, let's say, than what we have as a high voltage or as a low voltage. And depending on how much time we spend high or low, then we will have a different voltage value. So that's why we call PWM, which stands for pulse width modulation. Basically, we are modulating the width of pulses. And by that, we are adding average or removing average voltage. And that's pretty much it. If you do that into MOSFETs or into motors, sorry, into MOSFETs, then you will be putting different resistance in here, and then the current that goes through the motor will be different, and hence the torque, for example. And I let you, Edu, go to steppers. I stop sharing the screen, and then we'll come back to.
Which screen I'm sharing?
You're sharing. There's on the left side. There's
okay. Just a few things more on the motors, because we have seen with Óscar the theory about it. How that physically applies, how we change the current, for example, for a DC motor. You see on the pads, the cables, these are some semi-cylinders, and by cutting in half, this plate is connected to positive and this plate is connected to negative. So when the motor rotates, by its physical location of the copper, it automatically changes from positive to negative. All the time, for example, you see red, blue, red, blue, red, because by changing the location, automatically change the direction of the coil. So that allows to have a permanent change in the direction on the same coil, without having actually to change the battery terminals or the power supply terminals. You do this internally. This kind of motor is what we know as brushed, because these pads are some brushes, metallic brushes, the same as in a small scale, the same as the one that you use for cleaning your floor, because they are more or less the same. They are usually made of graphite, reinforced graphite and steel, and those pads get wasted. So actually the life cycle of a DC motor is short compared to other motors. They cannot rotate endlessly, because they have some friction parts that are those brushes, and those brushes, depends on the size of the motor, can be replaced or not. So I think it was Pablo who was asking how to actually a dynamo works. What happens if what you are moving are the magnets, because dynamos, they kind of do the opposite. In here you have the coils rotating. In dynamos, what you do is have the coils steady in a fixed position, and what you rotate is the magnets around. So when you rotate the magnets around, this graphic is actually, you see the attraction pole of the electromagnetic inductance. And if you wire around those little like flower pots, I don't know how to call this in English, you can actually conduct and move the electrons through them, because you can move the electrons by the coil location. And this, as Óscar was saying, you need to know how many turns of wire will augment actually the capacity of inductance or reduce it. It's not the same using a really, really thin wire than using a really, really thick wire. It will change completely. For example, if you use a really, really thin wire, but you change a lot, when you have a lot of turns in the same space, you will produce lower voltage, but with higher amperage. And in the opposite, if you have a really, really thick cable, you will produce a higher voltage, but lower amperage. And there where we come, for example, on actually the motors, the DC motors, rewinding the motor is something that is really, really common. Usually, for example, all the swimming pools motors, you never buy a new one. What you do is you open up and you disassemble and replace the copper, because by the friction and the time and the heat produced, the copper gets wasted, gets burned. That's why, for example, they say you have a swimming pool or your community has a swimming pool, they say like the swimming pool is broken. Why? Because the motor needs to be replaced because it has burned down because of the heat dissipated by the own motor itself. And this is something really common in industrial motors. So what you have is a mass of wires, and let me make it big, this part. So what you have is a lot of these small semis bars that are actually those ones that you have to wire wraps of cable in circles between them. And you usually do it, but you clean the motor, of course, and you basically do is knitting copper cable all around those wires. And you can not only do this in a big scale, but you can also do it in a really, really small scale. That is something that is really, really, really common to do, actually, to design a motor to match your performance. Like right now, the market is really broad and allows you to actually like choose the motor directly. But sometimes for specific applications, you cannot do it. And this is actually the one of the definition of the motors, the number of poles, that is the amount of like wraps that you can do, and the number of turns. So actually a motor is defined by the number of turns and the number of poles. More poles usually means higher speed, more turns also means lower voltage. Something that you need to be crazy about, but it's important when you choose a DC motor or brushless motor, that they will see later what it is. On the other hand, the solenoids, as Óscar was stating, you can push the bar out. But when we call about physical application, you never change the direction of the current. You only apply one side is positive and the other side is negative. So if the bar comes out, how you can take it in when you don't have current? Actually, the normal way is having a spring to come it back to the main position. This is the common way. If you don't have a spring, what you can do is actually reverse the current through the wires. So actually change to reverse induction through the reverse polarity. So the little metal bar pumps in. So you can do it both ways, mechanically with a spring or by changing the direction of the current. When you how to choose a MOSFET, NP channel, etc. So one of the first things you need to do, for example, this is the Fab Lab inventory. If we go directly to MOSFET, I think we have some transistors around, is check what is the voltage or the difference voltage that you want to apply and the amperes. So for example, let's choose this one, in NCH MOSFET, this one. I go to this side. Actually, this MOSFET is super small and can dissipate 1.7 amperes. But let's go to the data sheet. The datasheet is here. So actually, these tell us first how to connect it. We have the gate, the drain, and the source, and we have the limits. So this MOSFET is rated until a maximum of 30 volts and 1.7 amps. But that is the maximum rating of the MOSFET. But let's go lower on the absolute maximum ratings. That I would say that is the more important part. So the maximum voltage that you can apply on the drain is 30 volts. The maximum that you can apply in the gate is 20. So it's not usually the case, but if your Arduino runs on 24 volts in the data pins, you will not be able to use this MOSFET. But yeah, that's usually not the case. We have the maximum drain current, continuous. So we can run 1.7 amps in a continuous way. What happened with DC motor, someone stated before? To switch them on, to start, you need usually a spike of power, and that usually creates a spike of voltage and a spike of amperes just to start it. So this component can manage 10 amps for a short amount of time. So if you have a peak in the current, it will not burn, it will resist. The pulsed drain current is actually like some spikes of current that can go through the component. And after we have the rating of power dissipation, etc. So power dissipation, it means it can dissipate 0.5 watts. And that's quite important because all the MOSFETs, they need to be cooled. You cannot run them, for example, at 1.7 amps for 3 years continuously. You need to cool them. And for that, you usually use heat sinks. So it's quite common to see the MOSFET with a heat sink to actually allow them to not overheat and by so burn it. Another technique is to use, for example, this is a normal high power MOSFET for 10 amps that you have a big heat sink. So usually when you open your for example, the hi-fi, your old hi-fi of music, you see a lot of MOSFETs to actually drain the current of the speakers, and they have big heat sinks because those hi-fis are meant to actually put a lot of power through the speakers, and a speaker is basically a coil. Another similar way is actually to have a big, I don't know if we can see here, but let's go to the datasheet. Let's go to a big one. For example, this one is 16 amps, is a lot actually. Oh, what is this? Oh my God, there is no datasheet on this component. I don't know, let's find another one. IC regulator, okay, let's go to this one. This is a 1 amp, not that much, but I know it has datasheet. Okay, here. So actually, you see these ones, they don't only have 3 legs, but they have a big pad on one side. This big pad is the tap. That the tap is usually in this component is out, but a lot of them is ground. So this small metal part, that in this case is this part, is big because of one reason. This needs to be connected with thermal paste or to the heatsink. So this is the dissipation path to allow all the heat transfer to come out of your circuit. And when you drive, oh, this is a regulator actually, but the regulator works exactly the same in the behavior of electric dissipation. Usually on the base of the datasheet of these ones, you have some recommendations on actually how to cool it down. So they state a size, like let's say a pad of 5 millimeter by 10 centimeters by 10 millimeters of when you have to connect this part solder to part of your PCB. So that part needs to be soldered to a big part of the PCB, not a trace. Let's say an empty part of the PCB, to allow heat dissipation. So actually you use your PCB board to dissipate and work as a small heat sink. This is when you use small currents. So let's close this part. So what happens if you don't do this and you run, for example, a big, more or less medium-sized motor? For example, a motor like this is a really standard one. It's a DC motor, more or less big, the one that you might use for a small airplane or something like this. If you run them with a TO22 MOSFET, that is something really standard, this might happen if you don't use a heatsink. Well, and it's really common to see this. And one of the main reasons you have to be really careful also with the MOSFETs is when you connect them to a breadboard. When you connect them to a breadboard like this, the heat dissipation of a breadboard is really small and it has a lot of resistance on the internal plating. So actually burning a breadboard with a MOSFET is something that is really easy. So watch out what MOSFET you use and what power you are driving or your breadboard meanwhile you prototype. And this is something that also when the PCB is older, you might also see really commonly. Actually, a lot of the electronic DIY household devices, like from vacuum cleaners to etc., they sometimes have MOSFET, they have SSR, depends, or relays to activate different things. Is actually one of the most common failure points of electronic household devices. MOSFETs, regulators, and SSR or relays. Why? Because it's what actually is managing all the power of that device. So if something breaks up at some point, I recommend you to at least open up and see what components, try to find out what components broke. And you will see that you can check the numbers and check what component it was. And probably it will be some of the power driving train of your component, of your electronic device. So we have another different part of motor, that is the stepper. A stepper actually is really similar to a DC motor, but let's say it's a combined DC. It's like combining two DC motors. You have one DC motor and you have the other DC motor. So in this case, we have three DC motors. One DC motor, two DC motor, three DC motors. So actually that are called the phases of the motor. So when you drive one, you align the magnet with that train. What happens if you control the order of driving the different DC motors? In this the case is 1, 2, 3, 1, 2, 3, tack, 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 and by so they make each time smaller movements, and those are called the steps of the motor.
Wait, in this case, it's not 4 because there are 4 directions.
4 directions, 1, 2, 3. No.
Horizontal.
Sorry.
So it's vertical, diagonal 1, diagonal 2, horizontal.
Sorry, it's 4. Yeah.
Ah.
Yeah. I don't know even how to count. I will go to high school again, or primary school, kindergarten. So actually, yeah, as he was stating, is 4 states, and that actually are called the poles. More poles means you can make smaller steps, and you can control with smaller angles of movement. But by so, you are also decreasing the size of the magnets and the size of the poles. That means each pole has less attracting power. So more poles on a stepper motor will allow you more resolution, but usually with half the torque. So a stepper motor works by activating the different poles in sequence and allows different degrees of rotation. So a stepper motor, each step is the minimum resolution. And for a normal stepper motor, this is a stepper online. That is the most common online driver sell for steppers. You can go, for example, and check NEMA 17, that is a really standard stepper motor, 0.9 degrees. Oh my God, the cell mask everywhere right now. So a stepper motor, if you go to the data sheet, this one states that the minimum step is 1.8 degrees. So that means it has, usually those ones have like how many poles? Actually, it's more or less easy to know. Calculator.
200?
Yeah, exactly. So we have 200 steps in each one. So 360 divided by 1.8. Oh, sorry. Multiplied. 360 between 1.8. So it's actually, we have 200 steps in each one. So actually, to make a full rotation of this motor, we need to make 200 times tick, 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 activating the poles. Inside the stepper motor, usually you don't have 200 because that will be a smaller one. So what we do is interpolation of the coils. Stepper motor, open. So a stepper motor looks like this, and what we don't have is 200. We don't have 200 coils. What we do is 200 small changes in the magnet. You see, and the motors, you can find them usually also, okay, that's weird, 0.9. In the standard degrees of a stepper motor are 1.8 and 0.9. Usually 0.9 motors, stepper motors, have more resolution, but they have less torque. And here you have a video actually on a guy that did his own stepper motor manually with 3D printed parts and nails. It's quite interesting. So how you drive a stepper motor? First, there is two types of stepper motors, unipolar and bipolar. Before, unipolar stepper motor was quite common. Now, each time is less common to use it because this has changed because on the way how we drive stepper motors. Unipolar has a big coil and it has another terminal between them. So actually, it can emulate to have. Actually, it has two coils, but they can be controlled like 4. So if you drive the current between this one, it's not the same than driving the current from this to this, than driving the current from here to here. So you can choose which one you control. What happened is much more messed up on the way that you need at least a lot of transistors. And in this case, H bridges, because you want to drive the current in and out on each one of them. And the bipolar is quite the standard now. So you only have one coil, and you drive the current in one direction or the other one. So actually you only need one H bridge and one H bridge. If you have a unipolar motor, that actually is really common in the Arduino kits to have unipolar Arduino motor, something like this. That is the EY, I think it's E25, I don't remember the name exactly of it. Vale. Stepper Arduino. Oh my God, really? This one. Okay, really small picture. Can I see bigger? No. So this, yeah, this one, 28V8 BG. This is really standard stepper motor that comes in an Arduino kit. This one is actually a unipolar. We have 6 cables. So this stepper motor, you can transform it into a bipolar one. How you transform that one into a bipolar? I lost the connection. What is the class? Here. So actually, just by taking the long coil and ignoring the central one. If you don't connect anything to that one, you are actually using it, a unipolar motor, as a bipolar motor, and it still will work. Just for information, this small stepper actually has a gearbox inside. So the stepper is even smaller, and what it does, it has small reduction gears to actually allow more torque, because this stepper is really, really, really small. But if you are curious about, actually the DVD, where are steppers and the DVD room stepper motors are everywhere. Actually, your DVD drives and CD inside, how to control the disc, they have small steppers, really, really small and quick, like tiny steppers, because we can control, without having so much complexity, the amount of movement, and we can go to estimated positions. So steppers doesn't allow a really, really high, where's the class here again? Steppers and mean to have control of position, and they can go relatively fast, but they cannot have super high speed. For example, a DC motor works much better at the highest speed as possible of the motor, the mechanical highest speed. And a DC motor usually works between 3,000 to 24,000 RPM, and some of them 30,000 RPM. The small DC motors that you might find in the Arduino kits or like in the lab, that we have a lot of types, they're usually rated between 6,000 RPM and 20,000 RPM. So it's quite common to actually reduce the speed of DC motor with gearboxes. And it's really, really common to find them. And actually that allows to run the motor at the highest speed, but the output to be really, really slow. And that makes them drive more efficient. More things. So a normal DC motor is driven just with a transistor or a MOSFET. But a stepper, we need to control each coil, each of the coils of the stepper, and we will have to change also the direction of that. So for that, we use what is called H-bridges, that allows to have double H-bridges that allows to have control. Right now, there are some chips like the LN293, but they don't have that much power, and unless you are making a chip circuit, it really doesn't deserve to control a stepper that way. What you want to use is what we call Pululu drivers. And there are a lot of types of them right now. And they look like this. So they are small breakout boards that integrates a lot of different parts. They integrate double H-bridges, condensers, and actually capacitors to clean up the noise. And what you do is connect one of the coils, the other one, you connect the same logic of your control board, and you connect the big power. And what you do is tell how many steps you want. So it's much easier to do it in the software way too. So actually you say, okay, by having one step, what is one step? High and low. The state, a high and low state, that is one step. 2 steps, 3 steps, 4 steps. And also we can change the direction by just stating the direction pin high or low. So we can rotate the motor clockwise or counterclockwise. So this kind of drivers, we call it stepper drivers, are really, really common right now. How to choose also these small guys? Based on the amount of power that you want to dissipate. There are much more things, and because right now they are getting smarter and smarter, and you can control them. But what you need to always know is what is the maximum ampere that this can drive. So actually, it can only drive 1.5 amps. So one of the first things when you design a circuit is a stepper. I think I have the other one. Yeah, here, open. If you go to a stepper online and you choose a stepper, for example, this NEMA 17 is long and the coiling is different from other ones, and it's saying actually, this one has more resolution. It can hold 46 newtons per centimeter. quite not bad actually. It's like half kilo per centimeter. And the power consumption is 2.5 amps, but it's rated at a maximum of 2.9 volts. So actually, this is a weird stepper. Let's go deeper into here. And actually, it just states that the voltage of this stepper is 2.9 volts, but the amperes is 2. So actually, this stepper driver will not work for us. So we need to choose a stepper driver that will work. One that really commonly works for really high applications is the, what is this? Yeah, is one that is really similar, but allows, I know, until 2.5 amperes. So there is a whole wall of components to choose between these components. And we have servo motors. Servo motors are actually funny. A lot of people think that they are something really special, but actually inside a servo motor is just a DC motor with a reduction box. Servo motor inside, open, let's see. Here, perfect. Go back. So actually at DC motor, we cannot control the position. What we do is have a lot of reduction, and we work with a DC motor with reduction, and the last gear is connected to what? A potentiometer. A potentiometer, you can measure the analog signals, no? From 0 to 1023. So actually, when we rotate this guy, this moves the potentiometer to a certain position. And what we have is an integrated circuit that is usually really, really small, that is managing everything. So when this reaches 0, the integrated circuit says, okay, I have to stop. This is the 0 degrees. And I want to actually go from 0 to 90 degrees. This has been programmed to know actually the reduction ratio of this, and also can read by the potentiometer that applying, for example, 0.5 seconds of DC current by changing the polarity, so the motor changes the direction, will actually move the motor and get the readings in the potentiometer of the position. And when the motor has reached the position, it will stop it. Actually, it will not stop it. What it will do, you have seen the servos like jittering, like moving like this in certain position. A little bit, no? Like shaking. That is like cheap servo motors do that, because actually a stepper motor is never off. A stepper motor, what it's doing is changing the polarity, go and back of the DC motor all the time. Why? Because we don't want to move the position, but we don't want that the motor doesn't lose the position too. So actually we are applying force all the time really, really fast and changing the polarity of the motor. So actually we allow the motor to stay in the same position with torque. And actually when you choose a servo motor, you have the same. You have data sheets that are really, really important. And this page is really slow. I hate it. Okay, servo. So what you choose a servo is you choose one of the things is you choose first the angles, because some servo motors can move from 0 to 350 degrees, but the common is to be from 0 to 179 degrees, not even 280. Most of them, they don't reach 180 degrees. And they have the holding torque and the speed. So this one says that in 0.12 seconds, it can rotate the whole degrees of the range of the servo. This also states that this servo weighs 9 grams, so it's really small. Actually, this is the standard for hobby servos. And the voltage range of this servo is 3 volts to 6 volts. If you run more, you will burn not only the motor, but the internal circuit. And the internal drives, the internal gears are on nylon. That means it's quite bad. And it says apart, that is the holding torque. So actually, this little motor can go until 1.6 kilos per centimeter. So in a holding torque, in a distance of 1 centimeter, it can move 1.6 kilos. I don't know why you look at me like that, Oscar. Your face. So let's go, for example, to a big one that is quite common, that is a 46 kilo. Yeah, this is the more or less the standard for medium-sized servos. So actually, when you want to drive more precisely and much more accurate control, you want to choose a servo with metal gears, because the metal gears, they don't get wasted over time, and they obviously can hold much more torque. Actually, servo motors are usually quite powerful in the torque per weight relationship. What is torque by weight relationship? That means the amount of weight of the whole component by the amount of torque they can deliver. Servo are much better. Why? Because most of the component is a DC motor that is all the time on. But for example, this stepper motor is the opposite. You actually have kind of 2 DC motors, but you are only use 1 each time. So actually, that's why stepper motors, they weigh a lot, but they don't produce that amount of torque, even if they have torque. A DC motor of the same size as a stepper usually produces double amount of power, delivered power. So how to control the servo? We have gone before, and actually you control the same way as a PPM pulse that we have it here. PPM is pulse with modulation. Actually, we only have 10 minutes, and I think we can explain better PPM, PWM tomorrow because it's slightly longer. We have the last type of motors. That is what people call BLDC motor. Any clue of what is a BLDC motor? Open question.
DC motor without a brush.
Exactly. So usually also found as brushless DC motor. This nowadays is getting really standard, and each time is cheaper and cheaper and cheaper. So mechanically, it's slightly more complicated. In this case, instead of having in a diagram 2 poles, what we have is 3 poles. Why we have 3 poles? Because actually we don't have any brushes. Usually the stator, the part of the coil in a motor usually called the stator, is steady. And what it rotates are the magnets. They are free of rotation. So actually how we can reverse the current of the coil? Because we have 3 coils, and what we do is we power one. It's a concept between a brush DC motor and a stepper motor. But the difference is here we are using all the time all the coils, and we are using really fast. What's the good point of the stepper? We can switch on and off some coils. Here in the brushless, what we do is we have all the time 2 of the coils in one direction. So in this case, we have 2 coils that they drive the positive and 1 that is the sink. That means sometimes the power drives, like the electricity goes like this and goes like this. Other times you reverse it, and now it goes from here to here. And after the next stage is from here and this to here. So actually we are changing which one is the ground all the time in a common term. So usually you have 3 phases and 3 cables to control them. But that is the simplified way of how is a brushless motor. A brushless motor in reality is much more complex inside. Yeah. So that's the common way of a outrunner BLDC. So you have all the coils and you have the permanent magnets that they are moving around it. So actually why this is called outrunner? Because what it moves is outside. Let me show you a video on YouTube because it's quite simple, and this is common. This is right now is getting really common because one of the main business of this is the drone market that has pushed really forward the motors. Okay, no. So this is an outrunner motor. Oh my God, this video is super bad. Well, I think it can work. You can see this at home, but I don't want to lose too much time. Okay, let's. Oh, it was perfect. So actually, what part of rotates of the motor is the outside, and that makes to have much more inertia because you are moving a lot of mass in the more distant part of the motor, like the farther away from the center. That allows to have a lot of torque and rotate it really fast. Why it rotates really fast? Also because we have no hardware. So actually, as we don't have brushes, we have less resistance than normal CNC motor, and the only resistance that we have are the bearings of the central axis. So brushless is usually rated by the amount of power that can dissipate. That means the amount of power that the coils can run amperes and volts through it without actually burning the cables. So in this case, this motor, this is a terminology for batteries. This motor is rated until a maximum of 16 volts and until 30 amps. It means in a motor that is, this motor more or less weighs around like 15 to 20 grams. This motor can deliver can suck 30 amps of power, and that's a lot, and can run until 16 volts. Like the power by weight ratio of brushless motor is incredibly high compared to other motors. And we have the maximum revolutions. Oh, what are the revolutions? As Óscar was stating, when you increase your voltage, you increase the inductance, no? And by increasing the inductance, you increase you can control by that the speed. That's actually how DC motor it is. We control the speed of that DC motor by changing the voltage that we apply through it. The amperes are just the current that is eating. So actually brushless are rated by kV per volt. That means revolutions per each volt. So that means if this motor is 1000 kV, we multiply by the amount of volts that we use it for. So if we use 7 volts, actually this motor will rotate at 7,400 RPM. And this is slow. Like right now, stepper brushless motor, for example, brushless motor, this is really standard right now. It's a 3000 kV motor. Imagine they are rated until how much? They are rated usually for 16 volts too. So actually those small motors rotate until almost 60,000 RPM. That's incredibly high.
Eduardo, are they much more expensive than the brushed ones?
They are more expensive, but really deserves, because the life cycle of this motor is really, really good compared to a DC. Actually, for example, you know the CNCs you have some routers and spindles. The router is a DC motor. The spindle is a brushless. That's why a CNC with a router usually costs 1,000 and the spindle costs 7,000 in a big scale industrial application. I will finish determining the types of brushless, and we will keep it going tomorrow morning, okay? Tomorrow we still have class from 10 to 12 too, and this is the finishing of this lesson and also the outputs. We have another type of brushless that are called the in-runners. That is slightly more weird, but is for higher RPM, even higher RPM. So actually what the magnets are inside. It's difficult to see because usually don't see this open. Inside. Yes. So actually the coils are outside, but the rotating part is inside. Why we have the opposite configuration? because moving less mass closer to the center, we can allow to have higher speed with proper balance. So the in-runner motors are meant for higher, even higher RPM, but with less torque. This is for usually propellers and turbines to actually make really high rotations. How to control a stepper gets slightly tricky. Sorry, a stepper, brushless, because we need to control 3 phases at a time. It's similar in concept to a stepper driver, but it's different because usually we also need more current. And due that we don't have like 2 minutes, and this usually takes much more than 2 minutes to explain. We will continue this session tomorrow at 10. 10:30, like always. Okay.
I have just super fast question. Is it crazy to run the brushless like a stepper, like use it as a stepper motor?
Actually, no, it's not crazy. And actually, there are some type of brushless that what they do is they have really, really, really thin wires to actually compensate for the lack of magnets. Because steppers have a lot of magnets. You have 200 phases of magnets usually. So you can drive really small steps. But with brushless, they are called usually brushless for gimbals. It's really common to find them because they have a really smooth movement inside. I don't know if you can find photos of this. But they have really, really, really thin cables. The copper wire that is inside is usually like 5 microns in thickness. So they have a lot of turns to create a lot of inductance with a small voltage. And with that, they compensate by the lack of poles on the magnet point view. But to use them as a stepper, you need to, if it's a normal brushless, you have to rewind it to allow that. Right now they sell like that, like actually they are like this. They have more poles also. It's closer to a stepper, in fact, in the mechanical point of view, but you still drive them as a brushless. The point is, as you only have 3 cables and you can only change, you are rotating, what you do is like not only change the phases, but actually reversing the time at the same time the phases to actually control and compensate back. So the control is more complicated, and usually you need 2 ESCs or a ESC that is double to actually allow all that change.
Edu, is also there a difference in the noise they make, brushless versus non-brushless?
Yes, brushed motor have the friction of the brushes. Brushed motor brushes. This is funny to look for. Yeah, this is really the mechanical part. Actually, you have a spring pushing this through it, and actually you have friction. It's like metal sliding to metal. So actually, it's much more noisy. On the mechanical point of view, brushless have no noise. What happened is we drive the phases really fast. That means we are ta 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 ta, and that makes electromagnetical mechanical noise on the driving electricity. So actually, brushless usually using a really, really high pitch sound that is not that much by the mechanical noise of the bearing, but actually on the driver part, like let's say on the H-bridges part. But yes, brushless in general are like half the noise of a normal brushed one.
Very nice.
More questions? No? Okay. We will continue tomorrow. I will stop sharing my screen. Yes. Just to close, I recommend you to at least like go to Hobby King or I don't know, AliExpress and just look for different types of steppers, DC motor, brushless. So actually you know a little bit the numbers and allows you to choose, or to at least know what more or less those numbers states, and you can ask the questions tomorrow. Because actually how to choose properly the motors is not difficult, but you need to understand a little bit what the numbers mean. What is the holding torque? What is the standard start torque? What is the amperes, a maximum amperes? Okay. Well, I think the MDF has a meeting right now, actually, that you need to run for your, yes, you have second term kickoff, third term kickoff. And well, that's it. Let's see you tomorrow, guys.
Gracias.
Hasta mañana.
Thank you.
Deal.
Bye-bye.
Yes,
Thank
bye.
you. Bye bye.
Oh.